further ado, I would like to introduce Scott, who will be talking on Reveal Unmasking Malware's True Identity.
Thank you. So I'll be talking to you about Reveal. This has been like an IRAD project since last summer I started, and Praxis Engineering pushed me to present at ShmooCon, and we decided to open source this software in conjunction with ShmooCon. So here you go. I am a reverser of things, usually software, but sometimes hardware. But I'm not as good with hardware. Sometimes my hex wrench causes sparks on my computer when I apply it wrong. I'm interested in speculative execution side channels, Spectre, Meltdown, that sort of thing. I've produced reversing tool chains that were processing millions of executables a month and doing lots of analyses on them. And I have flipped bits using butterflies. Yes, I'm an Emacs user. I flip bits using Rowhammer, which is DRAM electrical circuits, and I flip bits using a hex wrench. So we're talking about binary signature diversity here. This is where the same code has different bytes. Malware will change the instruction sequences, the operations, and all the different things about the executable to make it so that the signatures that the AV clients are using no longer work. And an example here, you could even change the entire architecture. So I want to be able to match despite the entire architecture changes. You can see on the left of each block here, the bytes are completely different because x86 is different than ARM. Reveal started last summer when I participated in a binary signature diversity challenge. And in this challenge, there were red teams and blue teams. Now, Reveal that I'm showing you today is going to be a blue team tool, but in the challenge, I was on a red team. And as a red team, I was supposed to take malware and obfuscate it. Now, I heard about this contest really late, and I had a very, very ambitious idea, so I had to reduce it down to like the very simplest thing I could possibly achieve in like a week. And I was basically translating some of the functions into a different architecture. And I could only get it so that I could translate one function in the malware that they provided for us to obfuscate. So ideally, the blue teams should have been all over me and been like, yeah, this is this no other malware that we saw. But only 2 of the 6 blue teams actually identified me. So that made me think, hey, there's not enough blue team tools to identify malware. So why don't I actually produce a blue team tool? And what I will show today is 2 methods of preparing binaries for search and a framework for producing actionable information. So the first thing is sector hashing. You might look up sector hashing and get some academic papers. They're doing something slightly different with sector hashing. And what sector hashing does is it matches raw bytes and allows you to line up those bytes and find matching bytes across a corpus. But the academic papers typically just hash a binary and then search a whole like forensic image to see if it's there-ish. But my approach is to use match set analysis. And that we'll get into that on how it actually gives you much more useful information out of the sector hashing. I may have previously done sector hashing in a place where I no longer have access to the code. And today, Reveal is an open source rewrite of that. And that system was finding very interesting malware much better than the AV client engines could find. The problem, though, is Sector hashing only works on the raw bytes, and as I showed to you already, the bytes do change. So I came up with this idea of lifting the binaries with this technique called data flow slicing. And that lifts the binaries into a representation that is agnostic to the underlying bytes that implement it. And we'll get into that later. So as a bit of background, antivirus products. The client engines on your box are very weak. They have to make decisions very quick. They only have a fixed number of signatures. And they often just, like if they don't know the binary, they haven't seen it before, they'll just upload it to the cloud potentially. Even Windows Defender has a automatic sample submission. So the malware will automatically be, or any software potentially, can automatically be uploaded into Microsoft's cloud environment. And then all these cloud environments will run various frameworks against it. VirusTotal runs 50 different AV engines. They'll also run Cuckoo Sandbox. It's a detonation framework that tries to run the malware and see what syscalls and what domains it connects to and get all the information out of it. But what is really missing is the proprietary back-end engines that these AV companies are actually using to figure out what parts of the malware are the fundamental parts of it that they can use to then generate the signatures. Those are, they're proprietary, and people usually don't have access to those signature generation systems. They require lots of data sets and lots of analysis. But today I'm introducing Reveal, which sits more of like one of those back-end systems, and that's how it can outperform the client AV engines. But it will have the power to run on your laptop. Like I've run it on this laptop right here. So a high-level overview, sector hashing. You can take any files. You don't have to actually label them or know what they are. You just have to give it raw byte binaries. You can grab them from Linux user bin, from Windows System 32. If you have a known malware repository, then great. You can get more interesting things if you have a forensic media images and you've carved deleted files from disk and ingested them, or if you've scraped stuff from memory. Some shops have that type of malware on there. And then you can throw those bytes into the system and it will analyze it. So it takes those files and then it hashes all the sectors on those files. Typically I use 128 byte blocks. I've used 512 before, but you can use different block sizes and you can match smaller and smaller features if you get smaller, but it increases the size of the database. But overall, we're stuffing all those things into a database that we can then later reference. Similar thing goes for data flow slicing. You can take the same files and extract the data flow slices and then stuff them in a database that we can later use to analyze. Then when we want to have a file of interest and we want to know, hey, what's in this file? If it's possible malware or if it's regular software that you're just reversing. With sector hashing, you need to do a rolling hash at this point because the blocks, the sectors that you found in your input files could be at different offsets in the other files. So the rolling hash just shifts the window by 1 byte and then does a lot of queries against the database so that you can match despite the offset differences. And then we go through the match set analysis. We analyze the set of files that are matching each hash, and then that helps us group them that have the same set of files to identify the unique byte ranges here. With data flow slicing, that lets us, actually, we're looking at pieces of functions. So we can identify potentially inline functions and modules I'm not quite at this point yet, but this is an ambitious research project. And then we can identify all the unique components, because the malware, some of those unique modules are part of the malware. So why hasn't this been done before? Like, what if we just do function matching? This is a hard problem, and I'll get into why it's a hard problem. You have to go to this magical place called Theoryland. Theoryland is a magical place where things like 2 + 2 = 4 is true, and you're not encumbered by actual things like you're counting 2 cats or 2 seconds. It's just a theoretical place that everything is perfect, as long as you have the formulas for it. So for function matching in Theoryland, they'll be saying things like, if you give, for all the same inputs to a function, does this other function produce the same outputs? And then you can find, theoretically, the matching function. But this is like written like you have an infinite number of monkeys writing equivalent functions. And this is very hard to solve. So the problem space, is it the set of computable functions, or like they talk a lot about functions in this Theoryland as if they all terminate, because the ones that don't terminate are a lot harder to solve. So incomputable functions are those things that run forever, like your TCP networking stack runs forever, and in theory, they can keep going on and on indefinitely, so that doesn't match. And so some Theoryland resident probably says you can't solve function matching without first solving the halting problem, which, if you believe Theoryland, is a hard problem to solve. But I'm here to tell you, Theoryland isn't real. It can't hurt you. People love to optimize the use of their time. They'll just go to Stack Exchange and or search the internet for the first thing that implements the algorithm they have, and there really aren't an infinite number of monkeys versions of the algorithms. So the fundamental underlying algorithms are the same. There may be some instances of those algorithms, like if you have a factorial function, you can have the iterative one where you're just looping, or the recursive version of it. We don't care that those two algorithms are identical. We care that we can match each one independently, and that is useful information on itself. Another thing to know is obfuscators, when they rewrite these binaries, they must preserve the functionality. They wouldn't be very useful if they broke the binaries that they're obfuscating. So how the data actually moves throughout these programs has to stay the same. There has to be some notion of where the data goes throughout these programs. So we can reduce the problem set size. So Theoryland, it was determined whether all inputs map to the same outputs. But more practical, we could just match binaries in a DB. So what if we talk about just matching entire whole files? Believe it or not, some people have tried to do this. There are some fuzzy hashing algorithms, SD-hash and SSD, very old ones. Some people have come up with similarity metrics where the executables will have some similarity metric where they're similar enough that they'll be grouped together. And like if one executable was your malware, in theory it would be clustered and grouped to other instances of that malware. However, whole files, there are many different components in the files. And you may have a file infector virus at the end, or the malware may be the main app logic, and it may be tiny compared to all the other libraries and other things that are inside your library. And if you're using this fuzzy hash matching algorithm, then it's going to be weighted heavily towards all those other libraries and other things that are in it. So we have to break it down a bit more to find out exactly where, what parts are interesting. And we can actually match these individual parts. So what if instead of whole files, we just break it down into matching functions. I have two control flow graphs here of two different programs, or two different functions. And with a fuzzy hashing algorithm, they have to take whatever size input it is and scrunch it down to a single hash. So let's say you have this sort of output, and then they will do some similarity metric, like the number of bits that are the same here, and they might conclude that these two functions are the same-ish, which isn't a very useful metric, in my opinion. So, quick quiz. One of these functions is the common mem-move operation. It's just a simple move the memory from one location in memory to another. Which one of these two do you think is mem-move?
One on the right.
You're right, the one on the right. I guess I telegraphed that a bit too much. The one on the right, they try to optimize a lot of things. So there are so many different random things. You think a simple mem move would be simple, but this is like a heavily optimized function. So this mem move, some terrible things can happen because compilers like to optimize things, especially when you're doing lots of optimization flags. And there's this one thing called the, I'm calling the inlining monster. The one function, if it's only called once, or if it's a small function, the compiler will often inline it. And if you have higher level optimizations, then it will inline even more aggressively. So you might have this one function with all sorts of different things, and usually it's like main, or your main callback routine, that gets all these different things. I even have 2 copies of mem-move in here, so you can imagine these functions get really huge. So if we're gonna rely on a fuzzy hashing algorithm to match whole functions, then we're gonna have a bad time. It'd be like saying, and then a miracle occurs at step 2. So I say no to fuzzy hashing. I know it's very attractive, but resist it. It's warm and cuddly, but no, let's not go there. No fuzziness in the sector hashing. All right, the old way. So the old way, you have a file that you're searching for on the left, a database of files on the right. You can break files or functions into things, and things varies depending on the algorithm. Maybe you're doing little bytes in these fuzzy hashing algorithms, or you're using mnemonics of the functions to try and match functions by mnemonics. But these systems will merge these things together and then come up with like a similarity metric. So let's see this similarity metric. So we have 0%, 33%, 67% of the things match. And then the conclusion would be file 1 is the same-ish as file C. And a lot of times you'll see these similarity thresholds are really terrible because, because they're matching so many different things. They're mixing too many things into one bucket. This new way with match set analysis will directly put all those individual things into a database and then match those. So highlighting the same colors. And then we'll do this thing to look at the set of files that match each individual thing. Thing 1 here is matching files B and C. Thing 2 is also matching files B and C, and thing 3 is matching file A. And we can come up with a much more useful conclusion here. Things 1 and 2 occur in the same files. That means that we can see, hey, these things are always occurring in the same place. Maybe they're that inlined mem-move routine or a libc routine. We'd have to go dig into which files it's exactly matching, but without having to know which the names and other metadata on those files, we can actually group them and do this analysis here. Next, let's go over how sector hashing works. Now, sector hashing, I said, I usually In my testing, I use 128 bytes. I've gone everywhere from 8 bytes up to 512 bytes. But yeah, different sizes get different resolutions. However, there's a big problem. I can't like throw 128 bytes on a PowerPoint slide and have it be legible for you guys. So I came up with a simplified diagram where I have a 6-byte sector size on a 9-byte file. And I loosely modeled it after the Bobby Tables SQL injection. So you see Rob, paren, colon, drop. With rolling hash, you take your 6-byte window and then you shift it by 1 byte. And then you hash all of these different sliding windows of it. And then you might match different files in your database. So in this case, 2 files matched the first one and 10 files matched the second one in this hypothetical example. What we can then do is we can take those counts and actually apply a histogram over every byte of the original file. And we can see, hey, this spot is matching this many files, this spot is matching that many files. And then we can go a little bit further and we can see, hey, these are matching sets of files. So, and then we can go look up in our database. Perhaps we have names on them. I came up with these hypothetical names. Bobby Tables 1 and 2 matched the Rob part of it, and generic SQL injections are matching the other part of it. So then we can use this information to then go drill down and figure out which parts are the most useful parts. The part that's matching 10 files, the part that's matching 2 files. Depends on what exactly you want to match. So the output tends to be a bit verbose. So this is actual piece of reveal sector hashing output that before I optimized it. You can see different offsets in this file are matching progressively up to the full set, and then there's a long run of 120 hex bytes in the middle that match all of them. This is because the offset is different in each of these files that it's matching. Oh, by the way, this is 900 binaries in user bin, and I'm querying with bin ls. Bin ls matches very precisely 2 other files, so you see dir, ls, and vdir all at the beginning. Those are almost identical binaries. They just have slightly different things in the flags for the default display options of listing files. So those are matching really good. The rest of the files match at different offsets because they're different binaries. Now, this is a lot of output. We don't want to bombard the user with lots of different offsets. So I came up with an algorithm to group these things so that you can summarize them. And I can summarize all those 12 or so lines into just a single line of output. And this 512 byte region matches. So wait, what's this? Fuzzy set grouping, I'm calling that. I thought I said no fuzzy. The thing is, fuzzy stuff is okay when you're, and fuzzy and heuristics and all that stuff is okay, I think, when you're presenting something to the user. You want to summarize and condense down the output. It's not okay if it's your core algorithm and your core algorithm depends on your ability to herd cats. Next, I'll go over another optimization. When you're looking at raw bytes in a file, you want to make sure that everything is, all the context is local to that one thing that you're matching. In this example, we have a call to memset. However, in different binaries, that call can be, the memset and this function can be placed in different locations, and so the relative offset will be different. And we don't want to rely on things that are dependent on the overall binary layout. We just want to work with the local context. So what if we, okay, so here's an example of the match. So all the binaries are dropping off except for those 3 that are all basically the same, right across this one region. And we have all these short length matches. So if we zero that out, we also can condense down those many lines of output down to a single line of output, and it's covering a much larger region. So with zeroing out, this is like a really dumb thing. I'm just working on the raw bytes here. So I'm looking for every instance of E8 and zeroing out the next 4 bytes. I don't even have to use a disassembler or anything at this. And so this will better match these different things. So for sector hashing, the problem is the bytes change, like I said, when malware is using obfuscation. So we're going to move on next to the data flow slicing operation, which matches pieces of functions. So in theory land, there's this one problem called subgraph isomorphism, and it's considered very hard. So the graph on the left, you can probably see where it matches the graph on the right, because it's literally the right-hand side of that graph on the right that I drew for you. But as the problem size grows, this complexity grows a whole lot. But in reality, let's see what the reality is. It's not just one graph, but many overlaid graphs. Wait, does that sound easier? It sounds a little more complicated to me, but maybe we can exploit this. So for an example, it's very hard to come up with examples that fit on PowerPoint and that aren't the trivial, like, one basic block example. So here's my square multiply function that I wrote. It's just computing a to the x mod n. And this is what basic blocks you would have, and this shows the control flow between them. All those colored edges are control flow edges. And next, I'm going to show you a Ghidra plugin, Graph AST. This looks at the binary and shows all the different data flows throughout this function. It's a bit huge, a bit complicated. And I was thinking, hey, this data flow graph, all those terminal nodes at the bottom, they aren't, some of those are the conditional branches. They aren't, it isn't actually representing the control flow on the right-hand side. So I was thinking, hey, what if I can combine these two things together into like a super graph that shows both of these together? Are you ready for this? Do you think it's going to be a huge graph, combining all these together? There we go. Still a little bit of a tangle, but not nearly as bad. One thing I figured out is that if you, the Ghidra's graph AST, there were lots of different, like, single expressions in the nodes. So if you collapse them down into single expressions, then you can collapse a lot of the nodes. But another thing I noticed is that if you anchor these on expressions on basic blocks, then you can still have the control flow in here. And this is, I'm calling this data flow intermediate language. It's kind of like Binary Ninja's intermediate languages. They have low level, medium level, and high level ILs. I actually lifted this into my own intermediate language with a API that you can sort of work with at this level. However, this is still a little tangled, so I decided to do my manual PowerPoint magic to format this in a little bit easier to see data flow graph. And with this, the blue blocks are computations on one part of the function, the actual results. You can see it goes through to the return. And the yellow parts are the checking the exponent bits. And we can look at this as two different parts of the function. We can pull it apart, and I call this slicing, data flow slicing. And I have, this algorithm actually partitions the function into multiple pieces, and that avoids some NP-complete problems. And then we can just match those later. Another function, because getting examples is hard, I wanted a function that had some calls and structure dereferences. So I grabbed this PAM authenticate. PAM authenticate is a function that's called to check whether or not you should log in. It's interesting because if you flip a bit, then you can cause it to log in with the wrong password, stuff like that. But so this one has, structure dereferences and function calls. And I'm going to do my PowerPoint magic, and so I can cram two different versions of that one function into the same slide. Now, the one on the left is compiled for x86, and the one on the right is compiled for ARM. Now, this is kind of interesting. Their bytes are completely different, yet the graphs look very similar. And if you didn't have a keen eye, you might say they were the same. So we're getting there. So one of there are a few differences. So the first difference is the structure offsets are different. The x86 version has 64-bit architecture, so 8 bytes. So this first one, the +8, is accessing the second member of that structure, whereas on ARM, it's 4 bytes off because it's 32-bit. And similar for the other offset. It's almost twice the offset of the other one. Another change is the compiler chose to put the return, a separate return in this in the basic block on x86, and on ARM it chose to return all through the same function. And then another difference is all the offsets in the functions are different. Of course, it's different binary size functions, and all the functions are going to be laid out in a different positions. So how do we handle all these differences despite, and get the graph to actually match? So for structure offsets changing, we're going to normalize or zero out the offsets. For the control flow, we're going to transform to a common return. And for the function offsets, we're going to do a similar thing as we did for sector hashing and just zero out those offsets. So for structure offsets, we could keep them and still match. Maybe there's a stronger match there. We could zero them out, or we could divide by the word size on the architecture and then see if that matches. And we could throw all 3 of these at the problem at the same time and see if any of those match. So we're not limited to just matching the raw single option. We could change the control flow so that it all returns to the same one. And then we could zero out or replace it with a generic symbol for the functions. And then that would make it so that we can match based off the structure of the graphs. And then they would be identical at that point in this example. Another important thing is partitioning. So if there is indeed a change, they change their algorithms in different versions of the program. By slicing, the change will be isolated to one little slice, and all the other ones should still match in your entire function. So how do we match these data flow slices? We can't just match graphs directly. We have to come up with a text format for each one of these slices. And I use a process called canonicalization. If you're familiar with how digital signature systems work, they have the DER format, which forces a particular order on the digital signature. So you could take all the data, shuffle it up, and then put it through the same algorithm, and it will be serialized to the exact same format each time. Now, this is a little trickier because graphs only impose partial orders, but there's enough structure there that I can come up with a text representation of it that will be the same regardless of how you shuffled and organized your nodes, if they're indeed the same structure. And then we take the canonicalized text, and then we hash, and then we store it. So that was a long section. Everyone still with me? Did I lose anyone? All right. Now we're on to results. So you can wake up again if I put you to sleep. Now, I'm going to start off with some simple binaries. This is the same 900 binary repository. And these are matches with GDB. So you can see I had 92,000 only matched GDB and no other files. But 1,058 slices matched GDB and GDB server and no other files in the database. So if we wanted to identify those two files together, we could take any one of those 1,058 slices, and then it will be known to identify that. Or you could take all of them and match any of them. So you can come up with some powerful signatures, potentially. Another binary, Git. Git has an amazing number of matches against Git shell. I wonder why. And then the third from the bottom, BAT. Anyone know what BAT is? It's a version of the cat utility that just outputs files, but in the style of Git logs. So it makes sense that that file is matching. So the next slide, actual malware. You ready? So I downloaded 14 malware samples from a public malware repository, all from the same family of malware. And then I ran the data flow slicing on it with this async rat sample D. I labeled them A through N, all the 14 different samples. And we can see here that async rat sample D matches sample M with 83 slices and sample E with 60 slices. So if we wanted to match those groups of them, we could take any of those slices and match those pairs. And going up a little bit more, there's a set of slices that match all three of those. And this is just the tail of the output of my sorted output, so there's more different things that will match. Another thing that's interesting is when I looked at these files in VirusTotal, async rat sample D had terrible attribution. All the AV vendors were saying things like generic or suspicious. None of them actually had like an actual like, hey, this is this malware. Async rat sample M and E had respectively 1 and 3 of the 50 AV engines identified it as async rat, and a lot of them had other attributions like other names, because the naming community is doesn't have a great solution for matching all these. But the power here is that you can actually match these files and see the correlation with this system here. If you ran this and you didn't have like a name or an attribution for async rat, you could look at this output and say, hey, this file 1234 or whatever is also matching this sample here. What is this other one? And then you can go look at those files as a group. Now, you may be wondering, hey, I said I had 14 samples. Why are they not matching one another? And when I was doing one of my dry runs, someone told me I should have a confusion matrix, like a theory land confusion matrix. But this isn't a classification problem, so I came up with this match set correlation matrix. So this is just counting the number of slices between each one of these pieces of malware. And these are match sets that had only samples of this async rat and none of the other files in the repository. So this is counting all of those. So we have a pretty good correlation among all of those. And the malware is also, you have to remember, it's multiple stages. You could have the dropper and then the actual malware and then all the modules. So we're not necessarily gonna, one thing isn't gonna be shared code across all those stages. So we have to correlate and match across those. So we could pick a set of any one of these slices and for each of these, and then have something that will match them pretty reliably. Sample N is barely matching anything. There's only 2 against sample D. But you can see sample N only has 23 unique to itself slices. I think that's a really tiny file, so it might be like, I haven't looked into it, but it might be like a tiny little plugin module for this malware, for example. All right, plan features. So I haven't gotten around to actually tackling the subgraph isomorphism. Just partitioning the slices in a function, I could easily get slices that are matching like everything. So that doesn't really help us for matching those. We need to have a way of growing those slices with adjacent slices that that doesn't run into, thank you, that doesn't run into the massive complexity of doing all subsets and problems like that. So I have this idea where I can actually use the matches against the database to inform that growth of the graphs so that I can avoid those exponential growth issues. If it's matching the same set when I add these extra nodes, then I might as well use the larger node because it's a better way of matching. And this will help as I scale this whole system up, because right now it's kind of like a toy problem area with thousands of files. I hope to get it up to millions of files, so we need larger chunks that are matching, that match more precisely what files they're matching. And then I need to build the system to actually match the slices from signatures so you could drill down and pick it out. Unique parts, so there are a lot of unique parts in these slices that I was doing. A lot of that is due to, because I'm still keeping the offsets in some of my variations. So like it has the exact offset of functions that you're calling in some of those slices. So the large count there may be an issue, but if we can drill down to the unique parts that are matching that malware and no other samples, then maybe that would be a signature. But ideally, you would already have samples, whether or not you knew about it, in your repository that match that malware. And then you could use those pieces to pull it apart. Also, I haven't gotten to it yet, but I plan to do it, is extracting those inline functions and modules. Binary Ninja has recently started working on these features, feature called outlining, where they take compiler optimizations and they're going to try and do like common inline functions like that memcopy eventually and pull them out. But with this system, maybe we could automatically outline arbitrary functions and libraries that you have in your entire repository. So that would be a powerful thing for the reverse engineers to actually figure out. Another benefit is by getting rid of that fuzzy matching step, we are directly matching the individual features. We can actually trace back the offsets in the original binaries that we were matching, and potentially those might have debug symbols or reverse engineering annotations that you might have already done. So it would take a lot of work because you could be potentially matching tons of files, but you could summarize all that and potentially pull in debug symbols and identify, hey, this isn't just a function that we've seen in common sets, but it's been known as mem copy or this other random function that is in an arbitrary library. So I'll ask, what problems can you solve? Thank you. We solved function matching by reducing the theory land problem to a more manageable problem. I have an idea for addressing subgraph isomorphism, and we avoided fuzzy matching for our core algorithm. And results, obfuscation bypass, lifting to data flow overcomes the architecture changes. Zeroing and transforming slices helps us match even better. Identified some malware, and I've had better sample correlation than AV signatures because those virus total results were all over the map. Now, this project, it's actually on GitHub as two different projects. Reveal, the main project, just does sector hashing, so you could get started today if you don't have a Binary Ninja license. And the sub-project Flow Slicer uses Binary Ninja to lift and pull those data flow intermediate language slices and do all the slicing out of it. Currently, I run it headless, so you would need a corporate or bigger license, but I plan to make it so that you can run across a bunch of binaries with a regular license. And now I'll open it up for questions. Hey, Jordan.
All right, so I got a couple. I'll say most of them for afterwards, but I'm curious. You mentioned like on the accuracy of the matching. We've tried some similar stuff. We were having too much of an error rate, and so you put a couple of forward matches. How big is your repository when you were doing the accuracy of the matching? You were saying if you were pulling out just that corpus, like what was the total search space to show how accurate the matching was?
Well, the accuracy of the matching, it's a very hard problem because each individual slice has a different set of things that it's matching against. So it varies greatly amongst all the different individual slicing things that we have. So I'm not like identifying whole inline functions yet, but I need to go through all the different pipelines and maybe use workflows to make sure I'm doing all the better matching things there. I'll have to drill down as I evolve and make it more accurate matching. But it's very hard to describe it as an accuracy thing just because every single thing is matching. It's good to know that you have a set of things that you're matching against so you can drill down and know what it's doing so that we can then analyze it at that point. So I don't have to use any similarity or fuzzy metrics. I'm just directly matching things, and I kind of avoid. Sorry, what?
Sorry, I like that part of it a lot too. That avoiding the fuzzy matching introduces a lot of error as well.
Yeah.
Thank you.
Thank you.
Hey, Scott.
Hey, Jay.
I really like the combined graph, but if one was to operationalize this or attempt to operationalize this, say like maybe in conjunction with Jordan's stuff, how long, like what would you estimate the time to build up the corpus of data for the database to be, or like do you have an idea of what things you would use as a starting point for the corpus?
Oh, yeah. I was thinking it might be cool to like publish databases of common software with this analysis here. That way you could just download it and then start doing it. I'm not sure about how much copyright and like if I run very specific details on Microsoft binaries, like how much I can do there. But it would be interesting to have a public thing there. In terms of database processing speed, I calculate my laptop itself. It's i9 12700H. It can probably process about 500,000 binaries a month if I leave it running all the time. So we could potentially get lots of binaries going on there. All right, and I'm being told to stop, and thank you.